Hi, guys. I'm just letting people into the class from our meeting. Give me just a second. How's everybody doing? Nobody wants to say anything. It's okay. Okay. Let me just see if I can get the shot. It's too early to take a test. Well, luckily you don't have to take the test until 4. So I agree. It is too early to take a test. It's probably a little early to do math too. I agree. Although it's 10 o'clock Eastern time. Are you on a different time zone than Eastern time? Let's see. Let me do this and put this stuff up. Okay. I'm just trying to get my windows all situated so we can have our class. All right. So what I'd like to do is I want to finish up the. Give me just a second. I want to finish up. We have one last example for chapter 3.4. I'm going to do that, and then we'll talk about it. It's similar to the examples that we did yesterday with 3.4 continuous variables. And after we do that, like right now, like I'm sorry, hang on, letting people into the class. After we go through the example for 3.4, I'm recording it right now for posting it online. And then after we go through the example for 3.4, I'll turn off the recording so we can have a review session. And then you guys can ask questions if you want, or you're free to go and think about it and then come to office hours and ask questions. It's totally okay for you. We can decide that, but I'll turn off the recording so that what gets posted is just 3.4. Just some basically administrative stuff really quick. So tonight at midnight, right, our homework is due for the next homework set. Make sure you know that's 2.6, 3.2, 3.3, and 3.4. Okay, so there's quite a bit there that needs to be passed in. Make sure it's in PDF format so I can read it and then grade it for you. Also at 4 o'clock today, our test is available. Okay, it's like what we did with the quiz. Okay, where the test becomes available for a 24-hour window. And then, but once you start taking it, you have only a certain amount of time. It's a timed test, obviously. Our class time is 100 minutes. So you'll get 100 minutes to take the test and then 15 minutes to upload it. The 15 minutes is from our department. The department said only 15 minutes for taking pictures and uploading. As always, if you have trouble with uploading, you know, shoot me an email, let me know. You can send me an email of your exam, you know, the PDF of it, that's fine. But I'll just be look at the on our Blackboard page. So make sure you've uploaded everything there, okay? And again, like if you have troubles or questions during the test, email me. Certainly if you're, you know, starting it and you see a typo and you haven't seen an announcement typo, then definitely email me so I can fix it. I try to make sure that those don't happen, but sometimes it happens, even though I try not to let it happen. All right, so administrative stuff. Test today, starting at 4 until the window's open until 4 o'clock tomorrow. Okay, Eastern time. You can start it at any time. Once you start it, you only have 100 minutes to actually take it. So keep that in mind, okay? And if you guys, you can ask me questions this afternoon too. We also have office hours this afternoon as well. Oh, hang on, I'm still admitting people into the class. Okay, alrighty, so let's go ahead and finish up our example from yesterday from 3.4. So just to remind everybody, so this is still chapter 3.4. Right, we were talking about continuous random variables and their associated probability density functions. Okay, so first we talked about discrete random variables. That was in the previous chapter. Discrete random variables, just to refresh everybody's memory, discrete variables, they have very specific values, right, that we have to work for. When we set up our PDF, it's generally a table, or PMF. We can call it PDF or PMF for discrete, doesn't really matter. We set up a table because it's for when x is equal to this value, here's the probability associated with it. When we talk about continuous random variables, okay, I have a whole continuum of values within a given interval, okay, and that's usually defined by some kind of a function, okay. We're specifying these functions now, like the example that we're going to do in just a minute. This is a piecewise function with 2 linear portions. When we move on into other probabilities, later chapters, we're going to be talking about different types of functions that can make up a probability distribution underlying all of our statistical data. And we're going to talk about how we're going to manipulate those. So today, continuous random variables, generally described by a function, our values for x, okay, are on a continuum within some interval that we've defined. And I'm saying it's within an interval that we've defined because remember, our probability density function, the area under the curve, right, represents the probability, okay? And that whole area under the curve between these and these values has to sum to 1. Okay, remember we did that with discrete. We took all those individual probabilities, we summed them up, they were equal to 1, okay? So if our PDF, we take that whole area under our curve, we sum it up, okay, from A to B. I'm going to integrate from A to B. That whole thing has to be equal to 1. That's how I know I'm dealing with a valid PDF. Okay, some of the checks and balances that we have to do when we look at these functions. Okay. Anyway, also continuous distribution function too. What happens with those, right? That's basically like a running sum. Okay, I'm taking all the probabilities as I go along. Okay, and I'm summing them up. It's a continuous, a cumulative distribution function, and I'm accumulating probability as I'm going along. So I can look at my cumulative distribution function at a particular value, and all at that particular value, that represents all the probabilities up to and including. So that's like saying the probability that x is less than or equal to whatever that value is. That's how we look at our cumulative distribution function, okay? So with that said, that review, let's go back to example 4. This is on the example sheet, right, for our lecture examples for chapter 3.4. This is, I think, our last one. So we've got this piecewise function, okay, for our probability density function, and it's described 2 minus 4x between the range 0 to 1/2, 4x minus 2 between 1/2 and 1. I just like to plot this out just so I can visualize it. It helps me think about it. Plotting is optional. I do recommend it because it does help. Here's 1/2, here's 1, here's 1, here's 2. Okay, so 2 minus 4x, we're talking about a negative slope. So it's going to come down like this, and we're going between, here's our 0 and 1/2, okay? And then we're going a positive slope, 4x minus 2, from 1/2 to 1. Facing those. Hang on just a second. There we go. There. And then this goes like, I'm going to draw it off like that. Okay, so this is my first bit, and this is my second bit, okay? So this area under this curve between 0 and 1 is going to represent our probability density function. So part A, okay, so part A says, is this a valid probability density function? And the first thing that we have to look at for things to be valid is, are all the values positive? Right, because remember, it's not enough for our probabilities to range between 0 and 1. They have to be positive values, right? So we want to make sure that they all sum up to 1, but all the values themselves have to be positive. So if I'm looking, this range here, these values on my graph, so I'm going between 0 and 1, essentially. I'm going to put a little dashed line right here. So between 0 and 1, excuse me, all the values, my y values, right, are all positive values. So that's good. So all the values are positive, so that satisfies that one. This is between the when x is between 0 and 1. Give me just a second. There, okay, so in this range here, things are positive, right? Obviously, you
would be an example of when things are not positive.
Yeah, so you can see, like just this graph right here, right? The values. So if I were to continue this graph down, right? So say I were to say, well, just this function right here, this function, right? If I said between 0 and 1, we've got this function right here, right? I have a negative y-intercept, and then this value here represents my PDF. Well, these values here between 0 and 1/2, like if I'm just looking at, can you see that? Just looking at that portion of my function, okay? These y values are negative, okay? Which, I mean, we're looking at probabilities here, right? I mean, I need to be able to integrate that, and that's not going to give me a valid answer, okay? Because you want to be thinking about these things like this function represents a probability distribution of some data that we've been gathering, or some process that's happening out in the world or whatever. And I want all of my area under the curve to be positive because probabilities need to be positive, right? So if I look at, if I'm only describing this as between 4x minus 2, and I'm going to go from 0 to 1, this whole portion of it here, this half of the function essentially is negative, which makes it not a valid PDF, right? I could make it a valid PDF by like taking the absolute value of it, right? And that would flip everything up and it would make it, you know, a positive function. But I would have to do something to make it a valid PDF. Does that answer your question?
Yeah, thank you.
And then the other one too, so this is our first one, all the values are positive. And then I said for it to be a valid PDF, the values, the area under the curve, area under curve must sum to 1, right? So that's a big, that's also a big check that we need to do too. So we'll do that check. So I'm going to take my PDF and I'm going to sum to 1. I'll put a question mark because that's what I'm checking for, right? So I've got a piecewise function, which means my bounds of integration have to be broken up depending on which portion of the function I'm working with, right? So I'm going to say this goes 0 to 1/2, and I'm going to do the first one, 2 minus 4x dx, right? This is defined up above, plus, and then I'm going to go from 1/2 to 1, 4x minus 2 dx, and I'm going to integrate, and I'll use my fundamental theorem of calculus to actually work it. So I'm going to get 2x minus, this is 4x squared over 2, so this becomes 2x squared. I'm going to evaluate that from 0 to 1/2, plus, right, we're going to integrate this, so this becomes 4x squared over 2, which is 2x squared minus 2x from 1/2 to 1. Okay, when I plug in my values, right, so 1/2 and I subtract out 0, I plug in 1 and I subtract out 1 after I plug in 1/2, and I add everything up, this whole thing sums up to 1. Okay, so that also makes it a valid PDF. If like say all these values are positive, but let's say pretend you were asking like what makes it not a valid PDF. Let's pretend, okay, so all the values are positive, but maybe instead of going from 0 to 1, right, as a total interval, I'm going to go from 0 to 1/2, and I'm going to go from 1/2 to 1.5, say for example, right out to here. Okay, that means that I've got this extra bit that I'm summing, okay, in terms of my area under the curve. When I go to do that, right, 1/2 to 1.5 right here, okay, my bounds of integration, I'm going to get a total sum probability that's greater than 1, which will make it not a valid PDF. Okay, you could be given something like that and then asked to correct it. What is going to make this a valid PDF? You'll have to find the bounds of integration that are going to make this the total sum of the area under this curve equal to 1. Okay, so what bounds of integration are going to make that a valid PDF? It's going to have to sum to 1. Okay, so yes, now we can conclude. Yes, it is. Oops, sorry, you can't see that. Yes, it is a valid PDF. Everything's positive, and all this area under the curve sums to 1. All right. Harpy says, what's the probability that x is between 0 and 2/3? Right, so I'm going to look at, I'm going to write this down in math. So I'm going to say the probability, let's do this, that's better. The probability that x is between 0 and 2/3, right? I'm going to write it like this. Now, my issue with this is a great question. My issue with this is I look back on my piecewise function, right? And 2/3 is like right about here, okay, on my graph. So that means I need to use the first function, and then I have to use the second function, because the 2/3 is going to span both of those functions, right? So I need to be able to split it up, so I'm incorporating the correct intervals for my x values. Okay, so I'm going to say I'm going to go integrate from 0 to 1/2, the first function, 2 minus 4x dx plus, and then I'm going to go from 1/2, sorry, get this straight, 1/2 to 2/3, the second function, 4x minus 2, because 2/3 falls within that other interval. This whole portion, 1/2 to 2/3, falls in the second interval, dx. Okay, so then I integrate through with my power rule, 2x minus 2x squared, evaluated from 0 to 1/2, plus, oops, I'll write it down here, plus 2x squared minus 2x, evaluated from 1/2 to 2/3. Okay, so that's my integral, right? This is going to give me the probability that x is between 0 and 2/3. And I just evaluate this, right? I plug in 1/2, plug in a 0, plug in 2/3, plug in 1/2, add all the numbers up. I'm going to skip that part. I'm going to add all the numbers up, and I'm going to get 5/9, and that equals the probability that x is between 0 and 2/3. Okay, it's sort of a proof of concept. 0 to 2/3 is a pretty wide range, but it gives you an idea, right? If our values that we're looking for span both pieces of our probability density function, how are we going to handle that? Okay, so it's going to be 5/9. All right, our CDF. So let's do this. Okay, I'll give you guys a second to, I can't tell if you're still writing. I'll give you guys a second to write that, and then I'm going to turn the page over and start working on calculating out our cumulative distribution function. Make sure, although also, you know, on a test, we're going to be heading into more calculus as we go along in the semester. Make sure on a test that you show the antiderivative, okay? I understand, I know that a lot of calculators and other programs will actually evaluate this for you and give you a number, but it's required because we know that those programs are out there and even on your calculator, right, that we want to be able to see the antiderivative and that you understand, like, what the antiderivative, what's the bounds for evaluation. Okay, and then you can give your answer, right? You don't have to show all the nitty-gritty calculus steps or algebra steps, but I need to see this setup, and I need to see this, and then obviously the answer. Okay, all right. I'll scan this in later too so that you guys can have it. All right, so part C, what's our cumulative distribution function? Okay, so our CDF. So let me just write down what our PDF is again. So f of x, I'm gonna write this down. So this is 2 minus 4x, and this is gonna go from 0, oops, sorry, not to equals 1/2, and then I'm gonna go from 4x minus 2, and I'm gonna go from 1/2 x is less than or equal to 1. Okay, so now I just wrote that down. It's our PDF. So now we want to be able to think about our cumulative distribution function, which is our capital F, our random variable, right? And then we're going to initially call it as a function. I'll call it as a function of t, just so that we can kind of think, oops, sorry, so we can think about how we're going to be integrating it. Okay, so now I've got a couple intervals that I need to think about, right? So the first couple easy intervals are when x is greater than 1, right? And then also I didn't write it down when x is less than 0. So let's write down, we've got 4 intervals to think about. So when x is less than 0, my other interval is 0 is, x is between 0 and 1/2. And then I've got the interval 1/2 to 1. And then the last interval when x is greater than 1, okay? So our cumulative distribution function says, right, so before we actually get to, actually, do I want to leave this as t or x? I guess I called it a t. So before I get to my actual PDF, before things have kicked into place, I have not accumulated any probabilities. So when x is less than 0, my cumulative distribution function is 0. Likewise here on the other extreme, okay, after I've accumulated everything and I'm going off, like as x goes towards infinity, my cumulative distribution function is equal to 1, okay? So you can knock off the extremes at the beginning, right? And now we have to analyze, how am I going to think about my cumulative distribution function given the piecewise nature of this function to begin with? Okay, so let's think about this range here. So we're going to look at interval number 2. So this is between 0 and 1/2. Okay, so within this interval here, right, I'm going to take a look at, I'm going to say my cumulative distribution function. I'm going to go from 0 to t, right? Because I'm coming up with a function for this, right? So x could be 0, x could be 1, x could be 1.2, x could be, I'm sorry, it could be 1, x could be 0, could be 0.1, could be 0.2, could be all sorts of numbers. We want to be able to represent all of those possible numbers. We're trying to derive a function here. So I'm looking at the first interval function, first piece function here, okay, which we did before. So this is 2x minus 2x squared. Okay, and this is evaluated from 0 to t. Right, so when I plug this in, what I get is 2t minus 2t squared. Okay, so hold that in mind. That gives me the first bit. Now, our second numbered intervals. This is actually interval 3 in the list that we came up with. So this is 1/2 to 1 in terms of our intervals, right? So I told you before we were talking about like, well, have we accumulated half already? We kind of evaluated these numbers. Let's put it, I'm going to show it in a slightly different way to represent it. So I'm going to call f of t, right? This is our big F. This is our cumulative distribution function. So I'm going to write it like this. Oops, sorry, that should be an integral. So I'm going to go from 0 to 1/2. I'm going to write in my function 2 minus 4x dx. This bit right here is the accumulated, oops, sorry, I don't think you can see that, accumulated probability, right, that we've had so far from 0 to 1/2, okay? So we've already gone from 0 to 1/2 in terms of our functions, right? So I need to think about what's the accumulated probability that we've done. Be careful, what we just did prior to that was coming up with the function that's going to represent our cumulative distribution function. That's a function, okay? That says for any particular value of t, right? When I look at that particular, when x is equal to that particular value of t, that's going to give me the probability that x is less than or equal to that when I look at that function. Here, I'm looking at a number, okay, from 0 to 1/2. This is a specific number. This is how much probability we've accumulated between 0 and 1/2. Okay, I'm going to add that to the function that I'm creating, which is 1/2 to t. And this is the second half, 4x minus 2 dx. Okay, so now we're going to do the same thing that we did before. So then, let's see. Here, you've already seen the antiderivative, so I'm just going to skip some steps and write it all in. 2t squared minus 2t, and then plus 1, right? So we've got these constant terms, constant term from this portion, and a constant term definitely from here, right? This is a number, and I've got a constant term here. Add them all together, and I come up with this function here, okay? So now I'm going to put it all together with a bracket so that you can see it kind of consolidated, and then we'll come up with a sketch. Sometimes I think in our homeworks, we were asked to sketch things out or graph things out, so we'll talk about what that looks like. So I'm going to say my cumulative distribution function, big F of t, is going to equal to 0, 2t minus 2t squared, 2t squared minus 2t plus 1, and 1. It's 0 when, we'll say t is less than or equal to 0. I could have kept it as x, but we just we switched variables just so you can see different ways of portraying it. This is between 0 and 1/2, and this is between less than 1, and this is t is greater than or equal to 1. Okay. And I think technically we're a little bit loose. Actually, I should get rid of this one here. And then let's go ahead and graph out. So there's our cumulative distribution function as a function. Okay, so I'll put a box around it, summing it up nicely. And then let's just come up with a quick sketch so that you can see what this looks like. Let's do this off. Maybe I'll do it over here. All right. I'm running out of space. Okay. So now, right on this is my x, or my t, I guess we're doing it as a function of t. So this is 1/2, this is 0, this is 1, this is 1/2, and this is 1, right? So remember, everything prior to when our interval starts is going to be 0, and then everything after we're done accumulating is going to be 1. So it goes off in that direction like this. So now I'm looking at, I've got 2t minus 2t squared from 0 to 1/2. That's like a downward facing parabola. It's kind of like, goes like that. And then I've got this upward facing parabola. I'm being very loose about my sketch, something like that. You don't have to be perfect in your sketches, but we're just coming up with a general picture. This is the important part, right? This is our function that describes our cumulative distribution function. And this is a sketch of our graph, okay, for our cumulative distribution function. Okay, leave that there for you guys to finish thinking about it. And that wraps up 3.4. 3.4 is continuous random variables, their associated probability density functions, and how we calculate the cumulative distribution function. 3.3 was discrete random variables, their associated probability mass functions or density functions, depending on how technical your book is. and their associated cumulative distribution functions, how we analyze problems with them, okay, how we work it through, and how we calculate these things, how we calculate probabilities based on stuff. Okay. All right. So what I'll do is I'm going to stop the recording. I'll pause the recording.